Hello, hello. So, welcome. One second. Yeah. So welcome to week 9 of weekline live session for DSP uh, doubt session. And then I am Sai Dinesh. I am the PMRFTA for E33 digital signal processing. Okay. So yeah, let's get started. Week 9. So welcome to week 9 live session. So in this week, so basically the topics I'll be covering are mainly the phase response, all pass filter phase response, and some other subtopics, and then group delay, all pass filters, and all pass filters. Okay, so these are the topics that I'll be talking about in this. Topics that were discussed in class in the material, and the assignment questions are also based on these topics. Okay, so starting, so phase response, right? So let's say okay, h of z is some constant times b naught times pi k equal to 1 to m one minus zk z inverse by k equal to 1 to m 1 minus pk z inverse, right? So here the angle of the system, the phase of the system, angle h per j omega is equal to argument v naught arg of, so the summation actually, k equal to 1 to m arg 1 minus zk e per minus j omega minus summation k equal to 1 to n arg of 1 minus pk e per minus j omega, right? So yeah, so each pole or a zero, so the zk's are zeros and this pk's are poles. So the phase response from each zero or and each pole is actually uh, involved as a summation, right? Whenever we add a new zero or a new pole, so it actually, the phase response of that system will actually be added to the existing phase response of the existing system, right? So in the typical form, okay, so in the typical form, so typical expression arg of 1 minus e power j theta e power minus j omega is equal to arg of 1 minus r cos omega minus theta plus j r sin omega minus theta equal to tan inverse of r sin omega minus theta by 1 minus cos omega minus theta. Okay, yeah. So let's say we have a pole zero plot. Okay, and okay, and then let's say we have a 0 here at R. Let's say we have a 0 here at R, and then so this is some angle omega, some frequency omega, so the angle is e per j omega, and then there is a trivial pole. Okay, so here and then for a system which has real valued coefficients, phase response will be odd symmetric. Okay, so in this case we have a 0 at R, so here the h of z would be 1 minus R z inverse, right? So and then the angle h e per j omega is arg of 1 minus R e per minus j omega, which is equal to arg of e per j omega minus R minus arg of e per j omega. టెంపరేచర్ తగ్గిస్తే కంప్రెస్ అవ్వాలి. కొంచెం టెంపరేచర్ ఇంకా తగ్గించాలి. జస్ట్ అ మూమెంట్, సారీ. చేస్తే వస్తుందేమో చూడండి. ఆపేనా 2 minutes? అదక్కర్లేదు, ఇక్కడ ఆపించాను, ఇది ఆపించాను. Yeah, sorry. So this argument of e per j omega minus R is this angle, right? And arg of e per j omega is from the 0. Okay, so here this is theta 1 and theta 2. It's theta 1, theta 2. Sorry, it's the reverse. Theta 1 and theta 2. So here it is theta 1 minus theta 2, right? Now when omega, so when this actually shifts to, let's say okay, yeah, so when actually this omega is increasing, let's say the omega is going in this direction, so in that case it will be like this. The angles, both the angles are somewhat, sorry, from here, right? This way, right? So this angle, actually the theta 1 is actually increasing rapidly compared to theta 2. theta 1 increases rapidly compared to theta 2, which implies arc will be positive. Okay, that is for what? Theta greater than omega greater than 0. So actually the phase diagram will be somewhat of say this is 0, it will be somewhat like somewhat of this sort. Okay, now when R actually so this is when R equal to 1 and this is when R less than 1, right? So when R tends to 1, that is the 0 goes very close to the pole, sorry, to the unit circle, then the phase becomes linear. Yes, as R tends to 1, phase becomes linear, right? Now, okay, and also phi of omega is odd symmetric. Right. So important features are, so when R equal to 1, phase jumps by pi at omega equal to 0. Phase is linear, and finally this slope of the linear part is minus 1 by 2. So this is actually what I've shown above, the phase response shown above is actually wrapped, right? So this is the wrapped version of it, and then there is the unwrapped version. Okay, so the phase response shown here is actually the wrapped version, and there is an unwrapped version where the phase response is actually continuous, right? Now if what do I say, so if we express h e power omega as e of omega into e power j theta of omega, where a of omega actually belongs to the real field, right? So that is, it is real valued, meaning it can take both positive and negative values. So in that case, a 0 on the unit circle causes a sign change in a of omega and then avoids the discontinuous jump of pi. I mean, here we see that there is a discontinuous jump of pi, right? So this actually is a jump of pi, and that is actually not I mean, one would not be there if we consider it to be of this format, because the negative value is actually absorbed by a of omega when we cross that pole or 0, right? So this a of omega is actually called as the amplitude response or zero phase response. Okay, yeah. And now, so now this theta of omega is actually continuous. Okay, so one more thing is, next is that we have seen that when there is a first order when we call a first order pole on the unit circle, the phase changes by pi. Right, so similarly, if we cross an nth order 0 on the unit circle, then the phase changes by n pi. Okay, so one first order pole creates a phase jump of pi, that is at the origin. So at the on the unit circle. So here we have seen that on the unit circle we have a phase jump, right? So when we actually cross a second order pole, then we actually change a value of 2 pi. So this actually does not create a sign change, basically. Okay, yeah. So now next part is sorry. One second, just give me a moment. Yes, I'm sorry. Yeah. So when the phase response is constrained to be in minus pi and pi, minus pi and pi, then it is called as the principal phase. Okay, and it is denoted as R capital ARG H per G omega, and then when it is sorry when it is not constrained, it is known as unwrapped phase. Okay, so this is actually known as denoted as small ARG. This is actually not constrained to be in minus pi to pi. So whenever there is a jump like more than pi or something, it's still it's still continuous. It is unwrapped. So but then when we jump and then if we bring that to the minus pi and pi, then it is known as the principal phase, that is a wrapped phase, and this is the unwrapped phase. Okay, so let's take an example where okay, so let's say okay, and unwrapped phase would be so this is the unwrapped phase. Okay, let's say just remove this. Okay, okay, this is the unwrapped phase. Okay, yeah. Then but actually phase unwrapping actually does not remove the jumps of pi. It removes the jumps of so whenever there is a jump of uh, pi, it actually still remains after phase unwrapping, but when there is a jump of 2 pi, it gets removed because of the unwrapping, right? So it just continues below, but then whenever there is a jump of pi, it still is in that zone of minus pi to pi. So it's still so the unwrapping does not remove the jumps of 2 pi. So any jumps of pi still remain after phase unwrapping. Okay, Now, and one more thing is the phase response of a single complex pole is the negative of the phase response of a single complex zero. Okay, so basically, as we saw earlier, the phase response of a single complex pole was somewhat of this shape. The single complex zero actually has something of this sort. Complex zero. So, and then one more thing is, so this is actually omega, right? So when this change in the sign of the phase response from negative to positive or positive to negative actually occurs at the omega of the corresponding of the corresponding zero or pole. So here we have seen that, so whenever there is a pole on the real axis, when a zero on the real axis, the sign change occurs at 0. But then when it is a complex pole, let's say it is at r e per j omega naught, so the change actually occurs at some omega naught, basically, right? So this is clear. And then one more thing is, so in the last class we have seen the resonator, right? We have seen resonator, and then we have also seen improved resonator. So this resonator actually has how many poles? 2 poles, right? So here this h of z is actually 1 by 1 minus r e power j theta z inverse into 1 minus r e power minus j theta z inverse. So these are like complex conjugate poles, right? And then the phase response changes rapidly as we cross a pole, and we have seen this also in the phase response plots, right? So the phase response changes rapidly when we cross a pole. Okay, so so this was the plot of the resonator, right? So as we have seen in the previous class, so and also we have seen in the previous class what happens with the magnitude response of a resonator. We have talked about a concept with the magnitude response when there are two poles close to each other. What is that? Does anyone remember? So that is a hello. Is anyone there?
The gain will be increased, sir.
Yeah. So sorry, it closed. So it's known as the peak shifting. We have talked about peak shifting. Remember when when one pole of one tail of the one pole actually interferes with the another pole, so then we see a peak shift in the peak. I mean, peak increases, but then there is a shift in the peak. Remember that?
Yes, sir. Yes, sir.
Yeah. So the magnitude response was something of this sort, right? Middle. But then now the phase response will actually be of something of okay. So because of this pole, so this is 0, because of this pole, how does it be? So like, let's say this is minus omega and this is omega. I mean, if these are r e per j omega and r e per minus j omega, so this will be of thing of this sort, and this also sorry on this sort. So the overall will be something like, so I'll just remove these two. So the overall phase response will be something like okay, oh sorry oh something of this sort. So this phase rapid phase change occurs when there is a pole, when we cross a pole. Rapid phase change occurs when we cross a pole. Now, so these are the concepts related to the phase response of a single pole and a multiple pole, a single complex zero and a single complex pole, and etc. Okay, and then next week, so I think maybe we can talk about the assignment for a bit. So now, question 1 is the phase response of each pole or zero contributes an additive term to the overall phase response. Sorry. So question 1. The phase response of each pole or zero contributes an additive term to the overall phase. Is it true or false? Right, so earlier we have seen this one, right? So this equation, right? And we said that this is a contribution from a set of zeros of the system, and this is the contribution from a set of poles of the system, and these are actually added additively. So I'll just copy this. So we have seen here it is additive. So yeah, this is question 1. And then question 2 would be trivial pole or zero will not contribute to the phase response. Is that true?
Yeah, what is trivial pole?
So a trivial pole is a pole at the zero. I mean zero as in uh, just right at the origin. Actually, a pole or zero at the origin are known as the trivial poles. Right, so in the previous class we have seen that the trivial poles or zeros do not actually contribute to the magnitude response of the system. Now, is that true with the phase response? That is what we need to see, right? So, and is that true or a false? Like as we have seen earlier, um, let's say we have. I mean, we have seen, consider a single zero, right? And a single. So we have seen this example, right here. This example here, there is a trivial zero and a trivial pole. Sorry, trivial pole and then a single zero on the real axis. So because of this we have this part, and because of this pole we have this part, right? So again, one minus re per j omega, the angle, sorry, this is actually the angle e per j omega is actually no arg of, what is it, e per j omega minus r minus arg of e per j omega, right? And this is actually contribution from the trivial pole, right? So overall phase is equal to theta 1 minus theta 2. Question 3, what is it? The frequency response of a system with rational function transfer function can be with rational transfer function can be written as a omega a per j omega j phi omega, where a omega belongs to real and phi f omega is a continuous function. We just talked about it previously, right? So whenever we have a of omega which is real, then the sign change is actually absorbed by the a of omega amplitude response, and then what you are left with is a continuous phi of omega, right? So sign change is absorbed by this term. Sign change is absorbed by this term here. Okay. Yeah, and then question 4 would be, if all the zeros of an FIR filter lie on the unit circle, it will give rise to a phase response that is linear. True or false? So all zeros are inside the lie on the unit circle, right? So let's take the example hf1 equal to 1 for 0 less than n less than n minus 1. Then pitch e power j omega is actually equal to e power minus j omega n minus 1 by 2 n omega by 2 by sin omega by 2. So this, is it always linear? So what is, so this is the phase of the system. This is actually the a of omega, and this is e per j. So this is a of omega, and then e power j of I of omega, and then this is actually the phase response, right? So is it linear? That is what we need to see. So that is the question 4. And then question 5 would be, so a 0 that is inside the unit circle is reflected about the unit circle. Zero that is inside the unit circle is reflected outside, reflected about the unit circle. About the unit circle. So does this cause an decrease in the group delay? Does it cause a decrease in the group delay? Right, so and then there is a 0 here, r e per j theta, right? So 0 h of z will be 1 minus r z inverse. H e power j omega will be arg of e power j omega minus r minus arg of e power j omega. And then we need to find the group delay. The group delay is actually the derivative of minus the d by d omega of angle of omega. So this is actually this one, and then you need to basically derivate this with respect to omega to find the answer. This is the phase response. When you derivate the phase response, we get a group delay. Group delay is like how the phase shift is changing with respect to omega. How fast is the phase shift changing with respect to omega? So in order to calculate that, what do? We do a derivative. Like when we have a function and we want to know how rapidly the function is changing, that is basically the slope of that function at a particular point. What do? We find the derivative. So the group delay of a system is basically that. So when we have a system with a particular phase response, we need to find the group delay by derivating that phase response, right? So we need to find this and see if it actually decreases or increases. So all of this is actually the solution is there in the notes, if you see, right? So question 6. Now consider so one second, just open this. Yeah, consider h of z equal to 1 minus a z inverse, right? Where a equal to r naught e power j theta naught. Now the parameter r naught is such that 0 less than r naught less than 1. Now, so we have actually seen the magnitude response of this system in the previous class. Magnitude response of a single pole and a single zero. Do you remember that? So single zero, so let's say it is at theta naught, right? So at this theta naught there is a sharp valley and a broad peak. This is what we have read, remember? Hello?
Yes, sir. Yes, sir.
Yeah. So yes, so this is what we have, like, so no, this is how it was. So based on that, we need to find the solution. What does it say? The plot of h e power j omega square has a shape that is similar to a cosine function. Is that true? And then the minimum value of h e power j omega whole square, the squared magnitude response, is in the interval minus pi to pi. And then if r naught equal to 0.999, that is, it is actually tending to 0. Does it have a sharp valley and a broad peak? And one more thing is a filter design. So all of the first three parts are actually there if we by looking at the magnitude response of that single zero that we just drew. Okay, and then a filter designed using the given h of z has a very narrow transition bandwidth when going from pass band to stop band. Is that true? So as we see that whenever there is a pole, and then actually in the previous class we have also talked about how sorry, one sec. When we have when we have a single zero of this form, we have seen that this actually has a pole. A zero actually creates a narrow valley and a broad peak. So it will be something like a narrow but then a broad one. But as r tends to 1, valley becomes more sharper, is it? And then we have also seen that if we want a low pass filter, we can also put a pole at the pass band side, so that whenever there is a pole, there is a gain in the magnitude response, and whenever there is a zero, there is a attenuation in the magnitude response. So the low pass filter, so this low pass filter of the magnitude response, because of the zero, and that too if it is very close to 1, this becomes, as the closer it gets to the unit circle, the sharper it becomes. So I think with all of this we get the answers directly. So all these questions are actually straightforward just by looking at the shape of the single complex zero, or the magnitude response of a single complex pole or a zero. Now consider an FIR filter with a real valued response h of n. FIR filter with a real valued response h of n, that is defined in 0 less than n less than n minus 1. Its frequency response has the form h of omega equal to v of omega e power j phi of omega, and then e of omega belongs to r. As we again discussed earlier, that this e of omega actually absorbs the sudden phase change, that is the sign change in the phase response, that is absorbed by e of omega, and then what we have in phi of omega is a continuous function, right? So this is what we have seen earlier. What are the options that we have? Phi of omega in general a nonlinear function. So when the pole or zero is at the is very near the is on the unit circle, then we have a linear phase response. But then in general, what is it? So and then phi of omega can have jumps of pi. This is also an example you have seen whenever there is a pole or zero at the unit circle, right? And capital ARG, so arg h of omega, that is the wrapped phase response, is continuous in the interval 0 less than omega less than pi. Is that true? So depending on the location of the pole or a zero, there is there is a phase shift, and if it is on the unit circle, then we have a phase shift of pi, right? So that is again. And then one more thing is h of omega is an odd symmetric function. Here again we have seen that, again we have discussed earlier. So 1 to 3 parts are actually clear. So if 0 is on then the phase response is linear, but what is it generally? And then second part is phi of omega can have jumps of pi. Here consider the case of a zero or a pole on the unit circle, okay? And then arg h of omega is continuous in 0 less than omega less than pi. They can be jumps just right. Then fourth one is small argno. So this is capital and this is small, meaning this is unwrapped, right? So and then h e per omega is an odd symmetric function. Consider the fact that it is hint is h of n is real. So if h of n is real, is the phase response odd? So that's a hint, right? Now question 8. Now consider h of z is equal to minus a star plus z inverse by 1 minus a z inverse. This is a stable filter, right? So now the group delay of a given filter is always positive, always negative, is both positive or negative, or insufficient information. Which of it is true? So he said that this is a stable filter, meaning this mod A, so this mod, so pole is A, 0 is 1 by a star, but then it is stable, which implies mod A is less than 1. There is a pole should be inside the unit circle, and I mean, so if causal, mod A greater than 1 if anti-causal, right? So this is what we know just from the stable. He did not mention if it is causal or stable. Now a group delay is always positive or negative, or completely negative, or both positive. Excuse me, 1 second. Yeah, sorry. So is it both positive and negative, which is true? So how do we go about this? This is, and then what is this actually? This is an all pass filter which has poles, and so I mean this is of the form a pole and a 0 at the same angle, right? The phase response now depends on the, I mean due to a pole, so due to this pole it is of this form, but due to this 0 it is of this form, right? But then we also have a difference in the amplitude, is it? So now how does it change? No, right? So this is what we need to, you need to find out, right? So this is an all pass filter, and then all pass filters do not affect the magnitude response, but they do affect the phase response. So that is why they are actually used as the phase compensation, used for phase compensation, right? You need to find an example if you want to prove that, I mean if the information is not sufficient, you can just find one counter example which proves that it can be both positive, it can be both positive negative, or but also positive but also negative of this. I mean, for different values of a, it can be either both positive, both negative, or both. So if you can find one such counterexample, then we can say that it is a the information is not sufficient. So that is the hint that I give here. Okay, and then you need to figure that out for the assignment. Now question 9 would be h of z is equal to b of z by f z, which is causal, stable, and real valued, right? Frequency response of the form, again the one which is one where the frequency response is continuous, e power j phi of omega. At phi of omega is continuous, and then z naught be a first order zero on the unit circle. First order zero on the unit circle. So whenever we know that whenever there is a zero on the unit circle, let's say at some omega, then it is a what, linear phase, right? Now in the question, so it is a linear phase. This is how the response will be. The first one would be not plus. So we have seen that there is a phase change basically. Is that true or a false? And then second one is plus equal to minus omega minus. So just from this you can like directly see which one is true here. Okay, then third one would be d by d omega of a of omega at omega equal to omega naught equal to 0. We see that we have a constant. So since it is like this, the group delay is actually a constant, right? That is one. You need to find which among them are actually represent the system, the information that they are giving here. Okay, then question 10 is x of n is 1 by 3 power n u of n, and then y of n is equal to x of n minus 5 plus x of minus n plus 4, right? So take the z transform, which is y of z power minus 5 x of z plus x of minus of n minus 4, right? And if you see it like this, and we know the z transform of x of n minus 4, which is, so let's say it will be like 1 by z power 4 into x of 1 by z, or something like that, something of that form, not exactly sure. Okay, and then the group delay. So what is the group delay associated with y of n? That is what we need to find here. Okay, so let's say z power minus 4 x of z dash power minus 4 x of z dash, where z dash is 1 by z because of the time reversal. So we have y of z and x of z. Now y of z by x of z is z power minus 5 plus z power minus plus z power 4 here. Is it true? So actually this is 1 by z dash. So I mean hint would be find h of z. I mean here we know that this is 1 by 1 minus 1 by 3 z inverse. Right, so this apply this here, find this one and x of 1 by z, and then finally find h of z. Once you find h of z, you can directly get the group delay by derivating that with respect to omega. Right? Group delay by del omega. Okay. Yeah. Okay. So yeah, that is it. So we have talked a bit about the from the lecture notes, the main concepts about phase response and the response of a single zero or a single pole, and then we have solved, I mean I have given hints of a few of the assignment questions. Okay, so yeah, if you, is my voice audible? Yeah, okay. Yeah, so this is the discussion. So you can, if you have any doubts, you can ask me, or you can leave the class.
Sir, what about the 11th question, sir?
Oh, sorry. I thought okay. Yeah, I missed it. Sorry. Okay. So h of z is h1 of z into h2 of z, where h1 of z is given and h2 of z is given. We said that. So we have a particular h of z. Here we have zeros which are reciprocal, and then poles also which are reciprocal at 0.98, sorry, 0.8 pi and 0.4 pi. Is it? Yeah. So how is the, let me just write the question. Sorry, I missed the, I mean I thought there was no question, but it was my mistake. Yeah, so h of z is equal to into h2 of z, and given h1 of z equal to 0.98 e power 0.8 pi z inverse 1 minus 0.8 e power minus j 0.5 pi z inverse by power j 0.4 pi z inverse or minus 0.8 e power minus 0.4 pi z inverse. So how does the response, I mean the plot of this look? It's something like we have two zeros very near to the unit circle, and then there are two poles. I'll just write more clearly. Okay, so 0.8, right? At 0.8 we have two poles, and the angle is 0.4. So at 0.4 and the magnitude is 0.8, we have two poles, and then at 0.8 0.8 pi, okay, what is 0.4 pi will be something like here, and then 0.8 pi will be somewhere around here, where there are two zeros and 2 poles. So this is how the Z transform plot of this system is. And then second one is H2 of Z is 0.95. Oh, sorry, that is sorry. K equal to 1 to 4 Ck star minus Z inverse square Ck star minus Z inverse square by 1 minus Ck Z inverse square 1 minus Ck star Z inverse whole square, right? And then Ck is 0.95 exp j 0.15 pi plus 0.02 pi k equal to 1 2 3 4. So if we substitute 1 2 3 4 here, we see that the angle is increasing just a little bit, but then we have a second order 0 and a second order pole at 0.95. so basically this is of right. So yeah, so 0.95 is close to 1, and then we have at 0.15 we have two second order poles. So here at Ck star we have Ck star, 1 by Ck star and 1 second, yeah, at 1 by Ck star and 1 by Ck, zeros at 1 by Ck and 1 by Ck star, poles at Ck star, right? And 0.95 is the thing. Here we know that it is 0.95, right? So at 0.95 the poles are like, we have 4 closed poles which are all second order, and then again 4 conjugate poles also again second order, and then again 4 zeros which are exact replicas, which are exact the reciprocals of this thing, right? So this is how the Z transform of this system is, and this has a very simple Z transform of 4 2 zeros and 2 poles, and this is quite interesting. Now the value of the group delay tau g of omega for omega not equal to 0.19124 pi is, this is what we need to find out. So we know that how do we find those? Again, from one we know that the angle is again a additive term, right? The arg of b naught plus arg plus arc plus sigma arg with respect to zeros and sigma arg with respect to poles. Then we know actually the locations of the poles and zeros, is it? So now how do we find that? Poles and zeros. Just have to think about it. Yeah. So actually, if you see the lecture notes, this exact example, I mean, with the different numbers are actually given, and we see that the phase response is actually somewhat of, okay, I mean, this is around 50 and this is around minus 50. Okay, and the group delay is somewhat of this set. So this example is actually there in the lecture notes. Alright, so if you see the, I mean, I think you can get a hint from the lecture notes. I'm not exactly sure how to exactly determine the value of this, but this example is actually there in the lecture notes. Maybe you can refer to that for the hint of how to solve this. I mean, one thing would be find the individual responses for each pole and zero, and then find the group delay by derivating it with respect to omega at that particular value of omega. That is how you find it. Okay. Yep. Okay. Yeah. Alright. Any other notes?
Oh, for the last problem, we have the hint in the notes, sir, lecture notes, sir.
Yes. Yes. Yes.
Okay, so we'll check it.
Yeah. Yeah.
Okay, sir. Thank you, sir.
Yeah. Okay. Thank you.